Okay, here's the second part of the video solutions to the test. So problem number 5. Problem number 5 is basically an understanding of what standard deviation means. And statistics, again, you make a decision based upon the information you are given. So I would say really, if I really wanted an answer to this problem, I need more information. But based upon what we have and the understanding of standard deviation, this is my argument. All right, the average number of days that a construction worker misses is 8. Their standard deviation is 6. The average number of days that a factory worker misses is 8. And their standard deviation is 4. And if a random construction worker and factory worker were to be selected, which one would you expect to have had a better chance at missing more than 12 days? So you have to argue why you chose that particular individual. Well, let's look at what we know. For a construction worker, on average, they miss 8 days. Okay? Now, if standard deviation is sort of thought of upon as the average distance data is from the mean, the standard deviation is 6. So let's go out 6 units to the right, and we get 14. Let's go out 6 units to the left, and we get 2. Okay? Well, in a way, on average, now again, this is not 100% right, but on average, you would expect most of our data, or at least to be more closer to 8, and later on we'll find out in a probability sense that the data is around between 2 and 14. Let's just say it that way. But for our factory worker, we have the same mean, which is 8, but their standard deviation is 4. So if we go out 4 standard deviations, 12, we go out 4 in this direction, it is 4. So if you want to kind of think about it, on average, most of your data is going to be between 4 and 12. Most of your data for the construction worker is going to be between 2 and 14. So who's going to have the more likely chance of missing more than 12 days? Well, here's 12. And then, since the data is spread out more, you're more likely to find construction workers missing more than 12 days as opposed to a factory worker whose data is going to be more closely associated with numbers between 4 and 12, whereas these guys are further out. Standard deviation indicates how the more likely data is spread further and further away from the mean, the larger and larger the standard deviation is. So that's my argument. I would be choosing the construction worker as being more likely to be missing more than 12 days. And that's the best I could explain that to you. So hopefully that worked. Number 6, the mean for a distribution is 20. The standard deviation is 2. And we want to work with Chevyshev's theorem to determine the following. Okay, what is Chevyshev's theorem? Basically, Chevyshev's theorem tells us the proportion of data that is going to be within so many standard deviations of the mean. Okay, so it gives us an interval centered at the mean, and I just lost that because if I press too hard, it thinks it's an eraser. But anyway, the mean, and it gives us a percentage of data that is within a certain interval about the mean. There are a little bit further restrictions on it, and we'll discuss that as we go. All right, so I am trying to figure out the percentage of data that's between 10 and 30. I know the mean is 20. Since I'm trying to find percentage of data between two numbers, one of the things I might want to consider is Chevyshev's theorem. And if I want Chevyshev's theorem, the formula 1 minus 1 over k squared. K is the number of standard deviations I am away from the mean. The total distance between 20 and 30 is 10. But again, I want standard deviation units. So k is going to be 10 divided by the standard deviation, which is 2. and that is 5. Working with the formula, 1 minus 1 over 5 squared comes out to be 24 over 25. Throwing that into your calculator, you see that this is approximately equal to 96%. So my statement now is that at least I can expect 96% of my population data to be between these two numbers, at least 96%. All right? The only value we can't really work with is the fact that k has to be at least, it has to be greater than 1, because anything less than 1, we know 100% of the data is between the two. That doesn't really tell us something. So anyway, that's Chevyshev's. Anytime you're asked a question about the percentage of data values between two numbers, this is something you may want to consider. Now, in the next one, suppose we know that the distribution is bell-shaped, and we want to know the percentage of data that's between 14 and 26. Again, the 20 is centered, which we need for these types of problems, but the fact that it is bell-shaped, again, I can think Chevyshev's, but bell-shaped, I get a stronger answer to the problem by using the empirical table. By working with the empirical table, that's what the bell-shaped distribution suggests. Excuse me, I need some water. But the empirical table is what I should be working with here. But once again, I still need to determine the value for k. So the distance between 20 and 26 is 6. The standard deviation is 2. So the number of standard deviations from the mean I'm talking about is 6 divided by 2, which is 3. So I need to go look up in the table for the empirical table. Okay, this is an unedited video, so you get what you get. You don't throw a fit, right? But an empirical table, and I don't have it on the screen for you, but you should take it out your notes. From the table with k equal to 3, you see that 99.7% of my data associated with the distribution would be between 14 and 26 if I know this is a bell-shaped distribution. Okay? So the answer to that one is 99.7%. Next problem. Americans spend an average of 180 minutes online with a standard deviation of 20 minutes. And I want to find an interval, some interval, where at least 90% of all my population data is going to lie between. So again, I should be thinking either Chevyshev's or the empirical table. But since I didn't say anything about bell shape, I'm going to have to work with Chevyshev's. Chevyshev's tells me that if I can find, or I have an interval, it tells me the percentage of data that's going to be between those two numbers, right? I'm working backwards now. I'm giving you the percentage. I want the interval. So I need to figure out what k is by working with the formula. That is, 1 minus 1 over k squared has to be equal to 0.9 because I want 90% of my data to be in that interval. Okay? Now, if I solve for k, okay, so 1 minus 0.9 is equal to 1 over k squared. That tells me k is going to be equal to, well, if you work it out, k is going to be equal to the square root of 10. So k is going to be approximately equal to 3.162. Well, I'll add another space since I say keep 4 places. So that's what k is equal to. Now my mean, let me draw my interval again. My mean is 180. And again, Chevy says that if I am within 3.1622 standard deviations of the mean, 90% of my data is going to be between those two numbers, okay? So I need to calculate K times sigma. And sigma is equal to 20. So 3.1622 times 20 is going to be equal to, if I did my calculations right, 63.244. So what I'm going to do here is I'm going to add 63.244, and I'm also going to subtract 63.244 from the mean, and that's going to give me my interval. And my interval is going to be 116.76, comma, 243.24. Assume I did my math right. The logic's correct, but maybe the math, but I think the math is right. But anyway, again, let me just walk you through it again. I'm trying to find the interval that contains 90% of my data. So again, I think Chevy shells because it's not bell-shaped. But instead of having the interval, I'm finding the interval, so I'm working backwards. I know the percentage I want, so I need to solve this for K. Show yourself that K is equal to the square root of 10, which is approximately equal to this. Now again, Chevy Shells is talking about the number of standard deviations you're away from the mean. So I need to be 3.1622 standard deviations. The standard deviation is 20. So if I multiply this 3.1622 by 20, I get 63.244. That's the distance I need to be from the mean. When I add it, I get 243. When I subtract it, I get 116. And so here is the interval that answers the question. Problem number 8. We have a light bulb factory. We have 10 boxes of light bulbs which were randomly selected and tested to determine the number of defects in a box. And the following data was collected. So I had 2 boxes that had no defects, 2 boxes that had 1 defect, 3 boxes that had 2 defects, 3 boxes that had 4. I want the mean and the standard deviation for the number of defects. So I'm counting defects. So here's the data. Here's the frequency of the data. So again, I'm doing a sample, so I'm talking X bar here. So if I want to X bar, I'm going to take data times frequency, data times frequency, data times frequency, data times frequency, divided by the total number of pieces of data, which is 6 and 4 is 10. If I add this together, I get X bar is equal to 2. Alright, now that I have X bar, I now need the standard deviation. Again, what I'm going to do is I'm going to construct a table. Here's my data, 0, 1, 2, and 4. The next thing I need to do is calculate the difference between my data and the mean squared. 0 minus 2 is 2 squared. Again, you don't have to carry the negative sign because you're squaring. 1 minus 2 is 1 squared. 2 minus 2 is 0 squared. 4 minus 2 is 2 squared, right? So you get 4, 1, 0, and 4. But we have to take in consideration these data values were not given, we're given their frequencies, right? So 4 shows up 2 times, so I'm going to take into consideration the frequency. 4 shows up 2 times, so that's 8. 1 shows up 2 times, so that's 2. 0 shows up 2 times, so 4, 8. 1 shows up 2 times, so 1 times 2 is 2. The 2 shows up 3 times, so 3 times 0 is 0. 4 shows up 3 times, so 4 times 3 is 12, right? I think I said that backwards. But again, here's the calculations, but you got to remember how many times these pieces of data showed up. These need to be multiplied by the related frequencies. When you add this column, you get 22. So the standard deviation is the square root of that column divided by how many pieces of data less 1. 10 pieces of data less 1. We get the square root of 22 over 9. When you do the calculation, that comes out to be approximately 2.4444. So there's your answer for the standard deviation. There's the answer for the mean. The last question is we're going to look at a histogram and kind of interpret its meaning or some of the facts about the histogram. All right. The lower class limit for the first class. Usually a histogram is given in terms of their boundaries, the class boundaries. The class boundaries are reduced by half. At least for us, that's going to be the situation. So the lower class boundary here is not 99.5, but I have to add back 100. Add back a half. That comes out to be 100. The frequency for the third class, first class, second class, third class, the height of that one is about 18. That's what the heights of the balls represent, the frequency, unless it's a relative frequency histogram, where that would be the percentage of data in that interval. The midpoint of the third class, okay, well here's the third class. If you take 109.5, add to that 114.5 and divide by 2, that's what you mean by a midpoint, you get 112. So the midpoint is 112. I think there's one more. The upper class limit for the sixth class, so 1, 2, 3, 4, 5, 6. Here's the sixth class. Here's the upper limit. Well, you have to reduce the upper limit by half. If we reduce it by half, the upper limit is 29. There you go. Hopefully everything's correct. But there's no guarantee, and that does not excuse anything from a test. Again, these videos are unedited, so hopefully everything's right. If you do catch something, please let me know, and I'll send an email out. All right, so thank you very much, and good luck.